Hey, this is Math 7, Unit 1, Lesson 10, talking about changing scales in scale drawings. And so we're exploring different scale drawings of the same actual thing. Today's lesson was a little bit complicated, a little tricky here, so bear with me as I try to work through this with you guys today. So I'm going to try to review a little bit of your lesson and then kind of work through some of the problems as well. You began first of all by looking at a ruler and deciding the ones that would be appropriate to use in order to measure something. Just a way of deciding what's an appropriate measurement. So if you have an inch ruler here and you only have these little hash marks here, we notice we're only breaking it up into smaller sections of 1, 2, 3, 4, 5, 6, 7, 8. So we only have eighths really when it comes to an inch. So something like 5/64, we're not that detailed in our inches to be able to use that. 9 1/4, we definitely could break it up and use it there, no problem. For the centimeters, you notice we don't go out that far. We have 1 and maybe 0.1 or 1.2. We don't have this accuracy to go out that far in the decimals there or even there. So really our best measurements would be just the fourth and the 0.5 because of what we have. So just a way of saying use the measurement tools you have, but don't try to overextend them more than you need to. You looked at a drawing of about 2 feet there. You had a 7th grader's foot, and then next to the drawing of the person, the biggest foot in the world. And so perhaps this person's foot, maybe an average 7th grader foot, may be about 10 inches. Let's just go with that. If that's 10 inches, we notice this is probably somewhere around, well, there's a whole one there, a little bit more than that piece. Let's take for example, what's left here of this foot is from here to here, right? If I drop that on the foot there, I notice I'm somewhere around here, and if I measure that out of there, I'm almost the big toe. So 2 of those pieces chunk up there. So if this is 10 from here to here, half of 10 is 5. So what's left of this, if this is 10, what's left of this other part would be 5, and maybe the biggest foot in the world is about 15 inches. Just a way of playing with that. So it ends up being about 1.5 times larger from there to there, just messing with the angle measurements, the distances there. So we're going to do some playing around with measurements. So you began with some partner work, taking a look at a map like this, and you were given a triangle that your teacher asked you to go ahead and create a scale drawing for, and she gave you, or he gave you, some variety of measurements to use to create those scale factors. And so perhaps you had one that was going from 1 centimeter to 5 meters, or perhaps you were going from 1 centimeter to 10 meters, or even from 1 centimeter to 50 meters. The idea was you were just making a scale drawing using that scale factor. And as you did that, as you went through it, you realized that because of the way things were working, you got different answers here. So for example, your area might have changed quite a bit as you went from one to the other. Your area would have grown or decreased based upon the numbers that you were dealing with there. And so you might have had initially from 1 to 5, you might have had an area of, like, say 216 centimeters squared. And when you went to the 10, you might have had something like 54 centimeters square was your area. But by the time you got to the 50 was our smallest little shape here when you ended up doing your pictures, you ended up with a 2.16 centimeters squared. And so your triangles got, as you went along, got smaller and smaller. The larger this number became, the smaller the triangle became. I just realized I've been drawing down here the whole time. I'm so sorry. So we have our area here. We'll click again. If we had 1 to 5, 1 to 10, 1 to 50, the area ended up looking like less and less because our triangles got smaller. So our point was, with your scale factor, as that scale factor number increases, then our drawing tends to decrease, okay? Because it takes less of a measurement to represent more space. And that was kind of the key idea with that one there. Alright, so the idea here, looking at are you ready for more, try to keep it on the screen for you there, is if Noah and Elena each make a scale drawing of the same triangular plot of land using the following scales, make a prediction about the size of each drawing, and then how do they compare to the other ones. So for example, looking back at your first one, if you have 1 to 200, you know, back in our first one, when you did this before in your class, you might have had some triangles that looked like this, right? And so here are some samples here. if we're going to 1 to 200, this is 1 to 5, 1 to 10, 1 to 15, 1 to 20, 1 to 30. 1 to 200 is going to be even smaller. The larger this number becomes, the smaller our triangle becomes. It's just not going to work out too well for us. It's going to be really, really small, so we would say much smaller there. Now 2 to 25 is not a 1 number, but I could divide it. 2 goes into 25 one time, and I get 1 over 12.5. Well, 12.5 would be somewhere between these two triangles, wouldn't it? So it would be a shape between a 1 to 10 and a 1 to 15 if I was going to be looking at what it would look like if Elena drew up there. Now let's look at number like lesson 10.3 here. This is kind of the heart of the lesson today. A little bit tricky here, so I want to take some time with it, and hopefully I can help you understand this and go through it slowly. We have a scale drawing of a playground right here. It says the scale is 1 centimeter to 30 meters. So every time we measure out a centimeter, we can recognize that it's going to be about 30 meters. So I went ahead already and I took my marker out here and I went ahead and measured this and said that this is actually going to be 3 centimeters long from there to there. So that's 3 centimeters. This is also 3 centimeters here. This length here ended up being 1, 2, 3, 4, 5, 6, 7 and a bit. So I said about 7.5 centimeters. And this last piece right here ended up being about 5.5 centimeters. Not accurate, it's not perfect, but it's close. Okay, so again, I'm just estimating, getting it as close as I can. So that's where I began, is I first had to measure this to see, well, how long are these lengths? It wanted me to make another scale drawing of the same playground at a scale of 1 to 20. So I started with a scale of 1 to 30, and now I need to convert it to a scale of 1 to 20. Sometimes the best thing you can do is to find the original size or the original length of the shape and start there. That'd be a good place for us to start. So to do that, we knew that this was 3 and the scale was 1 to 30. So on that top line here, we knew that the top part would be 3 times 30, which would be 90. So I put up here in my initial drawing that this measurement was 90 meters. Over here, this length was also 90 meters. This length down here, because it's 7.5, 7.5 times 30 is 225 meters. And over here, 5.5 times 30 was 165 meters. So I started there, finding my original lengths for that. If it wasn't the scale, if it was a real one, it'd be that size there. From that point, then what you want to do is, our next step is, we're going to take our new, okay, we're going to take the original length, so the original length, and then we're going to multiply it by our scale factor. Okay, so our scale factor, our new scale factor. So in this case here, I would have lengths of 90. I have a length of 90 for B. A is also 90. D is 225. And C we said was 165. So what I'm going to do is I'm going to take those lengths and I'm going to multiply it by our new scale factor. What's our new scale factor? Our new scale factor is 1 to 20, right? So 1 over 20, 1 to 20. And then when I do that, what I end up getting is 90 times, or 90, I could do times 120, or if I'm using a calculator, I could do 90 divided by 20, however you want to look at it, is going to equal 4.5 centimeters. Okay? And the same thing here, 90 times 1 over 20, 1 over 20, 1 over 20. And so I do the math there, and so this height would be 4.5. For my long length here, what I end up with is 225 times 1/20th, it gives me 11.25, and then on the diagonal I end up with 8.25. So if I was to draw this out, I would end up with something looking a little bit like this. I'm going to start with my bottom line first of all, because I know that's my longest one, 11.25. So I'm going to go ahead and draw that right here. 11, that's 11, and 0.5 is there, so I'm about halfway, 0.25. On my vertical side, I'm going to be going up 4.5. So here is 4.5. And again, take your time when you're drawing. I think it's one of the key things your teacher's looking for. You're not just racing through it and just slopping something together there. So I have 4.5 here. I'm also going to have a 4.5, 4.5, and then my diagonal should be about 8 1/4. Again, it may not be perfect, but that's pretty close. I'm going 8 and a little bit more right there to get to 8 1/4. So I'm right here. Oops. So that's my new drawing. They want you to compare those two drawings, and what you did in class is you recognize that this one was just a little bit larger than that one. So again, the smaller the number for my scale factor, the larger my scale drawing tends to be. So the difference between a 130 here and a 120, this is going to be a little bit larger picture. So as a summary for the lesson, what we're looking at is we can say that we can use the original scale drawing to find the size of the actual object, step 1. Then we can use the size of the actual object to figure out the size of our new scale drawing. So again, the idea is that we're doing the scale drawing, find the original, then we multiply that by the new scale factor to get our new scale drawing. That was the idea behind that there. Now within that there, you could also look at the area, which you did it with your group. You look at the triangles to figure out the area, because areas can be a little different. For the area, for the new shape, you'll take your scale factor and you'll square that, which means multiplying it by itself, times the scale area to find out the actual area. So we're saying if you had some little shape like this, and your scale factor was 2, and you knew that the area was, I don't know, 4, then you would do 2 squared times 4 to find out your actual area, which in this case would be 16. So you're going to be taking a look at that concept in some of your homework problems tonight. So keep this in mind. Your scale factor squared times the scale area is going to equal your actual area. So in this sample, because it was 3 times as long, we took that 3 times and then we squared that to get the difference there. Alright, let's take a look at the homework then. So here's a drawing of a swimming pool. Where, I'm going to back out just a little bit here. Drawing a swimming pool where 1 centimeter represents 1 meter, right? So 1 centimeter, 1 meter. How long and wide is the actual pool? It's a good question. So we're going to do that first of all. We notice that it is 10 centimeters long. And so because it's 10 centimeters, that becomes 10 meters long or wide there. Now we get over here, and instead of being 5 centimeters now becomes 5 meters. So we'll say it's 5 meters. So that's our actual length and width. 10 by 5 is the actual there. Got it. Will a scale drawing of 1 centimeter represent 2 meters be larger or smaller than the drawing? Okay, remember what we said before. As I got bigger numbers, you know, a 1 to 1 is going to be the same. As I got bigger numbers, 1 to 2 in this case here, 1 to 50, think back to your triangles. The larger the number became, the smaller the shape, right? So will a scale drawing where 1 centimeters represents 2 centimeters be smaller, larger, or smaller? We would say that it's going to be smaller. And it's going to be smaller because 2 is a larger number. So let's make a scale drawing where 1 centimeter represents 2. Now, our first step we always said is find the original. Once you have the original, now we can go back. So in this case here, I know my drawing is 10, or my actual is 10. And I'm going to multiply that by the scale factor times the scale factor. And so because my scale factor is 1 to 2, my new length should be 5 centimeters. Now for my width, I take my original 5 times the scale factor, and I end up with 2.5 centimeters. And so I draw that out, and it looks like something like this. I end up with 2.5, so that's 2.5. And I go over here, and I'm going to go to 5 centimeters. So I go to there. I go up here, and I go 5 centimeters. 5 centimeters. And connect my dots at 2.5 again. And that's what I should have. So I have 5 and 2.5 centimeters for my new scale drawing there, which is a 1 to 2 is what I'm doing. Okay, the next question, number 2, so the map of a park has a scale of 1 inch to 1,000 feet. Another map of the same park has a scale of 1 inch to 500 feet. Which is larger? Well, we're looking like this. If 1 is to 500 is that one, and 1 is to 1,000 is this one, we've just said that the bigger the number gets, the smaller the shape becomes. Okay? So bigger number equals smaller picture. Okay? Think of it that way. And if again you want to think of it, or actually get this squared away, look at this. Here's an inch. That inch, because of this shape here, is how many feet? That inch is 500 feet. If I wanted to get to 1,000, I'd have to add another inch. And now this is now 1,000 feet. Okay, that's 1,000 feet. But in this drawing, what do we have? We have 1,000 feet. So again, what's happening is it takes 2 inches to make 1,000 feet. I have a bigger drawing. Over here it takes only 1. So the bigger the number, the smaller the drawing, the less amount of units I have to use to recreate that shape. Okay, let's go to the next side here. Number 3. On a map with a scale of 1 inch to 12 feet, the area of a restaurant is 60 inches squared. Han says the actual area of the restaurant is 720 square feet. Do you agree or disagree? Well, let's think back to what we said in our summary notes. To figure this out, we would actually take the scale factor and we would square that, and then we'd take that and multiply it by the area of the drawing, right, the scale area, and that would become our actual area. And that's what he's saying here. So what the guy is saying is that if I take the scale factor, square it, and multiply the area, I should get this. His thought is this. I take my scale factor, which is 12 squared, and I multiply it by the area, which is 60, I should come up with 720. That's the question. Is that actually the case? Well, let's take a look, because I'm not sure if that's going to be right. If I do 12 squared, 12 squared is 12 times 12. 12 times 12 is 144 times 60 equals 8,640. So I would have to say that Han was wrong there. It's not 720, it's 8,640 square feet. For number 4, if a quadrilateral is a scale copy of Q is a scale copy of P, created with a scale factor of 3, what is the perimeter of Q? This is a pretty straightforward one. The scale factor of 3 means we're multiplying everything by 3. So 7 times 3 is 21, 15 times 3 is 45, 15 times 3 is 45, and 25 times 3 is 75. When I add all of these up, I come up with 186 is the new perimeter. Pretty straightforward. And finally, looking at number 5, DEF is a scaled copy of ABC. For each, identify the corresponding parts of triangle. So angle ABC is here. There's ABC. So that would be angle DEF. So we're looking at this one, becomes that one. Angle BCA, so here is this one. We would say EFD, angle EFD. Segment AC is right there. That matches over here with segment DF. Segment BA is right there. Matches over here, segment DE. just matching corresponding parts. Hope that helps you out a little bit today. Have a great week.